Everyone, time for us to get started. As you know, I'm a big fan of this particular topic. So essentially what we're going to be doing is looking at linear approximations and then some things that we haven't talked about yesterday, and that's differentials. And this is obviously the last topic for this week. So a standard question would be to find the linearization function L of x. So you're being asked to find the linear approximation function, which I prefer better than trying to say the linearization. It's just a tongue twister for my brain. Right, so we're being asked to find the linearization function. You'll be given whatever this function happens to be. In the question I'm picking, it's going to be that one. And you'll be given a value to center it on. So in this case, we're going to approximate that exponential function with a straight line called L of x, and we're going to do it centered at 0, which means it will be essentially quite good at accurate at estimating the value of this, but close to 0, right? So when we say centered at 0, we mean it's good for things like 0.2s and 0.17s and things, but don't use it, for 22, and these centers can move. Well, really it's just a nice little process. You start with the function that they gave you, and then you need to differentiate it. The functions themselves for the most part won't be that ugly. Hopefully you recognize this as a chain rule, where that guy there is the inside function. So when you differentiate it, you get e to the 8x times the derivative of 8x, which is that. In this case, you'll need to know the value of the function at 0 and the value of the derivative of the function at 0. And this one ends up being e to the 0, which is 1, and 8e to the 0, which is 8. And so we're pretty much good to go. There is a formula for calculating, for finding, I guess, the linearization function. And it's that guy. And in this case, it's going to be f of 0 plus the derivative at 0, x take away 0. That guy was 1. That guy was 8. And so 8x plus 1. And for some questions, that's you finished. That's the only thing they ask you to do. They don't even get you to use it. And question, well, let's do another one, I think. That one I just did was basically a version of question 2. Let's do another question where you're only going to find the L of x, right? They're not going to use it yet. So question 3, or at least my version of question 3 is going to do that. Let's suppose f of x is the cube root of 2x plus 1. And we're going to center at, let's see what I want. At 13. So, what shall I do? Well, I guess the first thing I need to do is to rewrite this fella in the format that's going to make differentiation easier to understand. We've seen this before, right? If you want to differentiate a square root, you turn it into a half power. If you want a cube root, you turn it into a third power, things like that. So this is really just a chain rule, nothing too spectacular. There's your inside function. So if you want to find the derivative, you multiply by the power, and then you reduce the power by 1, and then you finish by differentiating the inside function, which is 2. In this case, we're going to get 2. So this is me really just doing style points. This in turn will become 2 over 3 times the cube root of 2x plus 1 squared. Not very pretty, but we can do it. I'm going to change to red for emphasis. I need to know the value of the function at a, which is at 13. Well, 2 lots of 13 are 26. 26 add 1 is 27. So we're basically finding that, which is the cube root of 27, which is 3. And the center value, the a number that we use, is exclusively always going to be a value that makes this thing and this thing easy, right? You don't want to try and estimate a cube root by using a value that's a cube root of 7, because, you know, cube root of 7's, you don't know what that is either, right? So you're just changing your problem from one issue to a totally different but equally bad issue. So you would never do, for instance, a equals 1, because wouldn't that be the cube root of 3, which is no use to nobody. So these aren't random, these are specific. Now, to do the derivative then, I'm going to use this guy. So it's 2 over 3 times the cube root of 27 squared. Now the cube root of 27 is 3, so the cube root of 27 squared is 9. So you get 3 times 9. And so you get 2 27ths. So that's what the derivative would be at 13. Okay, that's us got the two numbers that we need. Value the function at 13, derivative at 13. So the linearization function is f of a plus f dashed of a, x take away a. In this case, the value of the function at 13 plus the derivative at 13, x take away 13. That guy is 3, that guy is 2 27ths. We want exact values here, so I won't turn anything into a decimal. I'll just have to try and live with the awkward value. Of course, didn't plan ahead here. Well, the final answer would be 2 27ths x, and if you take 3 and take that away, you're left with 55 27ths. Or at least that's what I get in my head, but you can check it later. And there you go. Now, didn't we talk about what that is yesterday when we said, you know, that's the equation of the tangent line at an x coordinate of 13. So, I mean, couldn't you simply just plug in the original function into Desmos, plug that guy into Desmos? I'm making no attempt to be accurate, but can you imagine that was the cube root guy? That was f of x. And here was 13. Shouldn't that guy be a tangent line that looks like that? If I could draw better. If you do that, this is just a check. If you do it and the guy that you think's a linearization function's up here, wouldn't that be an indication you're wrong? Or if it went some weird angle like that, that would be an indication it was wrong. So in a test situation, at least you can check that. In a day-to-day homework situation, doesn't WebAssign just tell you you're wrong? So I guess you don't need to really check, but it's good to be able to understand how you could check without WebAssign's assistance. Are we comfortable about the process of calculating linear functions? So if I went and said f of x is cos x, and I wanted you to find it at e equals pi, would you be comfortable about the process to do that? You feel good? Okay. Looking for some feedback there, but at least you didn't shake your head. I'll assume that's a sign that it is good. So all I'm going to do next is add one more level. Let's say this guy here. We know that's a linearization function. I could say for part B, use this function to estimate e to the power of 0.8. Now you have to be kind of careful when you do this. For some situations, 0.8 will be the x, right? But you've got to remember the function that we started with was e to the 8x. So if you wanted to get that guy, wouldn't you be essentially evaluating e to the 0.1? So what I'm trying to get at here is, if you want to estimate this, you have to know the real value, right? The proper value of x that would generate that number. Now that I know it is that guy, I would evaluate it at x equals 0.1, and that would be my estimate, little squiggly equals lines for that. And this fella is 8 lots of 0.1, add 1, and that ends up being 1.8. So my estimate for what that is equal to is about 1.8. And again, I can check that. Some estimates are better than others, but here we go. E to the power is 0.8. Should be not 1.8, but wouldn't we at least hope if it's in the ballpark, you know, 1.9 or something? And the answer is pretty bad. Nothing wrong with that. It's just not a very good estimate. Did we do some really good estimates yesterday, like the sine of x was really good? So why is this one so poor? Some functions are better at linear approximations than others. So before we do one of theirs, which is a nice one, let me show you some of the functions that don't work well with linear approximation. If you get a function that bends a lot, if you do a linear approximation, let's say at here, can you see it doesn't take too long before it's really quite far away from the curve? So there's no technical name, well there is, it's called curvature, but I mean, basically you don't want a function to be too, inverted commas, curved. Can you see the problems with curvy functions? You don't want functions, would you agree, to have vertical asymptotes? It doesn't take too long. For instance, let's suppose that's where my tangent line is. Do you see that vertical asymptotes, especially on this side, don't they get really big really quickly? And therefore your estimate could be really bad. So, and the third one, which is really not a problem with the curve, suppose you get a nice curve and you find the tangent line, which is basically the linear approximation. Don't estimate it too far from the center, right? So that's some of the hiccups or issues with it. Let's show you a nice function that doesn't have any of those. So this is question 4. And we have got a nice, we call anything nice. We have a nice, whoops, wrong thing. We have a nice function. It's a square root of 4 take away x, and it's being centered at 0. So Let's find its linearization function. Since it's a square root, I'm going to call it a half power. And the value of the function at 0 is the square root of 4, which is 2. Now I'll differentiate. It's going to be 1/2 4 minus x. That's the inside function. So it's 1/2 4 minus x, reduce the power by 1, times the derivative of the inside function, which is -1. So you get -1, this guy to the half, you get -1 over 2 square roots. If you want to find the derivative at 0, it's -1 over 4. It's -1/4. So we'll do the first part of the question, which is find the linear approximation function, f of a, f dash of a, x minus a. Now the value of the function at 0. Right? The derivative at 0, x take away 0. And the value of the function is 2. The derivative is -1/4, and that's just x. Yeah, that'll work. So the linear approximation function to this square root close to 0 is a pretty good fit if you use that. And that's part A. Now part B gets us to estimate some square roots. First one we're going to estimate the value of is 3.9. You have a little squiggly mark and where beside you put the answer in here. Now look at the original function and look at the value we're trying to estimate. Do I plug 3.9 in here just because that says 3.9? The answer is no. What value of x do you need for this to become 3.9? Because that's the x you're using here. Right, so back to my question. What value of x do you need here to make 3.9 happen?
0.1.
Okay, so you identify what the x is. Sometimes the x will be 3.9, right? And other times it won't, right? Depends on the question. So here it's 0.1. So the linear approximation function is going to be that one. And that's going to be 2 take away 1/4, 0.1. And at this point, you do use decimals. And so it's 2 take away 0.1 times 1/4. And the answer I get is 1.975. So my estimate for the square root of 3.9 is 1.975. Now let's see if this one is a good approximate. Square root of 3.9. There, would you agree it's a pretty close fit to 1.975? Now, why is the square root nice? If you think about it, aren't square roots pretty boring? Aren't they just gentle curves? Gentle curves are good, right? Nothing changes very quickly. It's not, the squiggly ones, right? And it's definitely not got a vertical asymptote. Now, if you wanted to find an estimate for the square root of 3.99, you would ask yourself the same question. What value of x needs to go here to get that number? And the answer is 0.01. So here's a little truism. Right, see that guy there? He's dead close to 0. See this guy here, isn't he very, very close to 0? I'm going to make a prediction that this one is going to be even more accurate than that one was. right? The closer you are to whatever the center is, the more accurate your linearization function is going to be, right? It's going to be correct to a lot more decimal places. So if we evaluate it at 0, 0, 1, it's going to be 2, take away a quarter of this guy. It's not what I'm looking for. 2, take away 0.25, which is a quarter, 0.01. And the answer I get this time is 1.9975. This one drifted at the 5, didn't it? It was like 4.9 or 4.7 or something, right? It's good. Let's see where this one drifts. The square root of 3.99 is 1.9974. Do you see it's moved up one decimal place in accuracy? In fact, if you rounded that off, isn't it almost the same number, right? It's damn close to being perfect. Any questions? Are we comfortable about that? Now, if I wanted to, but it's really a time issue, and they have a third part to this question where you plug into Desmos this guy, you plug this guy in. It'd help if I drew the thing accurately, right? You plug this guy in, and shouldn't you get a perfect match at whatever number we're talking about? Actually, at 0, it would be over here, so be there. Because at x equals 0, you have a 4 there. I won't do that one, it's pretty much the same. So let's change tack a little bit. Suppose I have a function that I want to find a linearization from. So this is going to be pretty much the same. Suppose I'm interested in, what shall I do? I like square roots. The square root of x squared plus 1, it's a nice function. And I'm interested in a, do I want that to be a 1 now? Probably not. So I'm trying to think of, there, not there. So, square root is x squared plus 16, centered at 3, and I want to do the linear approximation. So that part is pretty standard, so I'm just going to jump right in and do that. So it's going to be x squared plus 16 to the half power, which means it's a chain rule. And there's our inside function. You're going to multiply by the power, reduce the power by 1, followed by the derivative of the inside function. And that gets you an x, and that guy comes downstairs, and I will turn that guy into a square root. Pretty standard, right? Nothing too spectacular. Now I'm going to evaluate it at 3. I guess we'll do it here. The value of the function at 3 is the square root of 9 add 16, which is the square root of 25, is 5. And the value of the derivative at 3 is 3 over the square root of 9 plus 16, which is 3 over the square root of 25, which is 3/5. Nothing too amazing here. And now we'll do the linearization. So up to this point, nothing is different. It's very similar to previous questions. It's going to be the value of the function at a, the derivative at a, x take away a. and the value of the function is 5, and the derivative is 3/5, and it's x minus 3. So it's 5, 3/5 x, take away 9/5. That guy, that guy's going to be 1 and 4, so it's going to leave me with 3 and 1. It's going to leave me, I hope I did this in my head, right? 16/15. Well, let's just check it out. 5, take away 9/5. Turn that into, oops, yeah. Turn that into a fraction. Yeah, did it right. Now, at this point, nothing has changed. We've done 2 or 3 questions just like that. Now the difference. I would like to know for what values of x will my linearization function be accurate to plus or minus 0.1. So if I'm going to use that straight line, right, this guy here, I'm going to use this one. Why is that not showing? There. I'm going to use this guy. For what values of x will I be within 0.1 tolerance, right? So will I be able to get by with values of x, you know, close to 3, right? So 2.5 to 3.5. Or maybe I'll get away with 2 to 4. Or maybe I'll need 2.9 to 3.1, you know, that kind of thing. What is the range of values where I can be sure that I can use this guy and I know my approximation will be within that tolerance, right? The kind of thing engineers do, right? What kind of tolerance have we got? How do you think I'm going to solve that problem? Any suggestions?
An inequality?
Yeah, we could certainly do it that way. Yeah, a very messy inequality, but let's show you what it would look like. Wouldn't we want to know somehow or other for what values of x is this guy the same as, say, that guy? And so we do what? Some kind of the difference between them. Between that guy and that guy. Does that make sense? That would be the difference, because that's your error, and there's your inequality. Now, if you try to solve this, and that's essentially what you're going to do, it's going to be the function take away the approximation has to be within the range plus or minus 0.1. Does that make sense? That's essentially what that looks like. Now, I don't want to solve that. I don't like solving inequalities at the best of times, but I certainly don't want to solve that one algebraically. But that's the right thing to do. That's what we're going to do. We're just going to let a certain guy that we've used in lots of other situations that makes our life easy. And what we're going to do, essentially, is let Desmos figure out the solving of that problem. Right? So, let me show you how you would set it up. You go into Desmos, and you put in the original function, take away, and I'm just putting brackets around it because it's less work than doing the whole thing. And that is, I hope, because I can't type and look at the same time. There. Would you agree that's the function? And that's a linear approximation. Now we click out of that. it helps when you put a y at the front, or else Desmos doesn't know it's a graph. There we go. So far, so good. Now, if you look at this picture here, and we home in on x equals 3, what you're looking at, this red curve, is actually the error function. It basically tells you how far away from the right answer you would be. If you notice that really close to 3 isn't the answer virtually 0, right? Can you see how low to the ground that value is? So what I now do is I put in a y equals positive 0.1. Hopefully it'll accept that and not be a pain. Good. And then the other boundary is negative 0.1, which looks good. And the difference should be, well, in this case, that one doesn't matter. Do you see the green line never actually touches the curve? So I'm going to kick that one out, and I'm just going to focus on this fella. Do you see that the blue line is when you reach the maximum error? Anything beyond it, to the left or right, is going to be bigger than 0.1. So if I click on that guy, and I click on that guy, and back to this one again, can you see the values of x that you get? And the values that we got are from 1.834 to 4.353. Cool. So the difference between the two, the plus and minus errors, if one of them, like this one, never cuts the graph, then you can pretty much ignore it. And then you have a start value and a finish value. And so we now know, if I return back to my screen, we now know the range of x's. As long as x is between 1.8 and a bit and 4.3 and a bit, this linear approximation function will be equal to that guy, give or take 0.1. That's a pretty big interval, isn't it? Let's make it harder. Suppose they wanted give or take 0.01. Right, so in other words, you want to be good to what, the second decimal place? Now, would you agree that would shrink down the values of x where that would be true? The only change I really need to do is when I go back to Desmos, is don't I just need to change the upper boundary to that number? And then things get a little bit messy because it's quite hard to do the shrinking, right? So when things get to, I can't see the blue line crossing the red line, right? Because it's very hard to do. Go here and change these y values.
Professor, we're not seeing
Yeah.
Desmos.
You aren't? Oh, okay. Sorry. There. I'll zoom back in again. I just changed the y to 0.01. Now, if you look at that blue line, can you see it's almost the x-axis? And if you zoom in, isn't it quite hard to tell where the horizontal meets the red curve? So you have to tweak Desmos to help. And so I'm going to put 0 on that side. And then I'm going to put 0.01 on this side. And there, can you now see the blue line and the red line? Right, so you just tweak it a little bit. Sometimes you have to help it by telling it the y values. In this case, it's going to be there and there. And now we have a different interval, and the interval is from 2.614 to an x value of 3.405. And I will return back to our picture. as long as you pick values between here and here, your answer is going to be good to 0.1. From here to here, right, values of x from here to here, is going to be good to the second decimal place. So if you wanted to be really crude, as long as x is between 2.6 and 3.4, if I plug those values of x into here, the answer I get will be within 2 decimal places of perfect. And that's kind of useful to know, isn't it? I'm going to use this linear approximation function, but how accurate is it, right? Well, now we have a method of finding that out. We can tell you. And they do a funny little symbol, and it looks like that guy. Does anybody know what that little funny E symbol means? It's from set notation. You might have met it somewhere. It's you read it as the word belongs to. So x belongs to that interval. Or another phrase is a member of that interval. So that's just how you would say x is one of those numbers in that range. Are we good? Right. So an added level of question might be find an interval of x's where your function is to a certain degree of accuracy. So if I jump to question 6, you'll see that, and I'm not 100% sure where that guy am, so let me make sure. There we are. In question 6, they are asking you to prove that the inverse sine function is equal to that. So that's just a way of them telling you what L of x is, and it's your job to check it. So we would start, and it's centered at 0, which is fine. So what you would do is you would begin with this function, and then you would find the value at 0, and the inverse sine of 0 is 0. And then you would differentiate it, and you'd get 1 over the square root of 1 minus x squared, because we all know what the derivative of the inverse sine function is. And if you find that guy, you end up with 1. And then if everything works out correctly, this guy should just be x. Well, it should be the value of the function at 0, the derivative at 0, x take away 0. And that's nothing plus 1 times that guy, and it is. But there's nothing to write down because they don't give you a box where you say, yes, I have verified it. But if you wanted to do it, that's what it is. So someone has told us that. So what they're asking us to do is to find the value of x's. So it's within 0.1. So Desmos is going to be our go-to guy. So we're going to be basically finding when is the original function, take away the linearization function within plus or minus 0.1. And I have never done an inverse sine function with Desmos, but I'm pretty sure I know how to make it happen. And it's going to be something that is about to annoy me. But here we go. Inverse function, arcsine. Take out the E, arcsine doesn't need an E. Arcsine minus x. And of course, there we go. And in this case, don't we also, I better change my values to plus and minus 0.1. In this case, then I'm going to go here and tell Desmos what the y values are. So it's going to be -0.11, not just make sure I can see it, and +0.11. There we go. Click out there. And where's the +0.11? I thought I put that in. I did. Oh, I had an extra 0. That's what was wrong. There, much better. Right, can you see it? Maximum value up there, minimum value down there. Do you see in this case, actually the plus and the minus were both used. Depends what the curve does. So at this point here, I have, you can use values of x up to -0.754, and you will get the accuracy that you need. And you can go as far as, oh, +0.754. There you go. As long as x is between here and here, the linearization function using x will be accurate to 1 decimal place. That's pretty good, isn't it? If you're centered at 0, you can get roughly 3/4 of the way plus and minus, and you're still going to be, well, I guess 1 decimal place isn't great, but at least you know how accurate you're going to be. Now, if you wanted to make that ridiculous, like, 0.0001, couldn't we go back to Desmos and just change the y values and let it tell me where the x and y is? If I wanted that accuracy, I'm making this up, but wouldn't you end up with something like -0.03 to +0.03? In other words, the range of x's that you would be able to say that that is true are very small, right? They're only a small window where that would work. Is that cool? Let me get my gripe over with then, because I said I don't like it, and I don't. So I got to say it again, because it is annoying me, and I want it out of my system. Americans use feet. Nobody else does. Americans use Fahrenheit. Virtually nobody else does. America does some really stupid things, and they do this guy. That is the inverse sine function notation. That's what you should use, and you do. But for some reason, you still use that. And I looked it up because I was curious why that notation, right, first started. Because actually, that was the original way to say inverse sine. And all I have discovered is that there's 2 reasons. The first one is printing presses. When they were, I mean, we're talking 1700s printing, right? That was very difficult for printing presses to print. That was easy. But once printing presses could do that, you really lost the need to do that. But evidently America got caught in a time capsule. So when you became independent in, what, 1776, you were using that. And then those nasty British people with better printing presses started doing math books like that. And Americans said, we don't do what those darn English do. We're going to stick to arc science. And I made that up. But that's the only reason I can think of why anybody would use an archaic system. But that is, right? It's a really, really old-fashioned way of writing that guy. So will you stop doing it so I don't get annoyed, right? So when you go to university and or if you go to university and you do math and your professor gets up and he says f of x is arc sine, will you politely say to him, I believe in 1780 we changed that over to the inverse sine function, and that's much more modern way of doing it. And after you get kicked out of the class, you should be able to at least feel better about it. Because I would. If I'm a math class and some professor did that to me, I couldn't control myself, right? As they drag me out screaming, I'd be shouting things like what's that guy? Benedict Arnold was a patriot. Well, from my perspective, he was. Okay, I have drifted. Let's focus back on the job. So each of these questions that are coming, so for instance, I'm not doing this one, I'm just going to set it up for you. In question 7, they tell you that that guy can be a linear approximated by this guy. And they seem to like centering at 0, which is fine. They can center it anywhere, but 0 is good. This you're meant to prove. And then they do that, what interval thing. And their go-to accuracy seems to be 0.1. Right. So if you were going to do that in Desmos, you would do y equals 1 plus 4x to negative 4, take away that guy, and then you do a positive 0.1 and a negative 0.1, and can you pretend it looks like that? And wouldn't that be your, oops, wrong one. Pretend it's that, and there's one of your values, and there's your other value down here. Right, you'd get the boundaries. Right, so where the horizontal lines cross the function. And question 8 is basically the same thing. That's all I want to do with linear approximation functions. Are we good? Right. So you can do it for any function in the universe. Some are better than others. Remember, we don't like curvy curve functions, and we don't like functions with vertical asymptotes because they don't work for a lot of x's, right? You need like almost on top of it to get an accurate answer. So now we're going to move on to something we haven't talked about, which is also in this section, which are called differentials. If you take a function, say y equals x cubed, and I asked you to find its derivative, you could use Leibniz's notation and say dy by dx equals dx. I could have said f dashed x, it would have been the same thing, right? Dy on its own and dx on its own actually have names. This guy is a differential in y, and this guy is a differential in x. So if you wanted to say that, you could say dy, but if you wanted to be a little bit more formal, you would say the differential in y and the differential in x. So that's what differentials are. They're dy and they're dx. So if you got a question and it said y equals x cubed, find the differential. When there's no reference to which one of these two it is, we always assume that they mean y, even if they don't say it. So if somebody just says find the differential, they mean find dy. So let's figure out what the answer is. And you are going to be amazed and rather surprised than other adjectives I can come up with on what it is. There is your differential in y. when you look at that, isn't there a very big temptation to think you've just done some version of cross multiply? It's not cross multiply in the same way that that's not a real fraction. But in a lot of mathematical ways, doesn't it behave like it was a fraction? So I'm being very lawyer-esque, right? It behaves like it's a fraction. It's not a fraction. Don't tell any professor I said that that's a fraction, because they'll laugh at me. But it works in a similar kind of algebraic way that a fraction does. So it means these questions are dead easy. Aren't they? Really? So, suppose I went and said to you, find the differential of that guy. Well, you would say its derivative is e to the 6x times 6, and then you'd get the differential. Now, compared to some of the stuff we've done, is that not very straightforward? I mean, it's as straightforward as something could be, I think. Now, you can make life more difficult by making the functions uglier. So you might get this guy to do. I want to know this one's differential. Well, if I'm going to differentiate it, I really need to write it as a half power, agreed? And I'm going to stick to Leibniz notation and write the derivative as dy by dt. And that would be multiplied by the power and reduce the power by 1, followed by the derivative of the inside function, which in this case is negative 6t. And then I'd spend a few lines making it look pretty. Although after a while you can kind of cut out lines of working, can't you? Go from there to there pretty quickly. And once you've finished the differentiation, your last line is that. Are we good? Basically, once you've found the derivative, isn't there just one more line to get the differential? Right? So the most work you're going to do is in finding the derivative. So suppose we did theta squared the sine of 2 theta. Okay, I want to differentiate this fella with respect to the variable theta. Which of the many methods that we've looked at over the last few weeks does this one fall into? What methods or methods, maybe more than one, that I would use to differentiate this guy? Say again, please. I thought someone said something, I just didn't catch it.
The product rule?
Yes. And so that's going to be F and that's going to be G. It's not the worst product rule in the world, so I might not actually do this at the side, but when things get messy, don't I tend to do something at the side and break it down a little bit. So F is going to be that guy, so its derivative is 2 theta. And G is going to be this fella. And when I differentiate this fella, I do get the cosine of 2 theta. Do I get anything else? So if you differentiate the sine of 2 theta, is the answer just the cosine of 2 theta, or is there something missing?
Well, it should be 2 to the 2 times cosine of 2 theta.
I agree. So technically speaking, isn't this a product rule with a little baby chain rule? So we can now do the f dash g plus the f of g dash. And then move on to the next step, which would be 2 theta times the sine of 2 theta plus theta squared times 2 cosine of 2 theta. I can pull out 2 theta as a common factor, and that will leave me with the sine of 2 theta plus a theta cosine of 2 theta, which is nice. So the major work is just differentiating. You want the differential. It's basically just the derivative with a d theta tagged on at the end. Are we comfortable with finding differentials? For the most part, isn't it really just differentiate and then do an extra line? Okay. So let's show you one more thing that they do with differentials. In fact, it's one of the reasons why we even bother to calculate differentials. I want you to think of dy as representing the difference in the y values when theta varies. So d theta is how much the theta changes, right? So theta is 0.2, d theta is 0.2. It means you've got a number and you go 0.2 either side. So if you go 0.2 either side, what will be the range in the y's? So it's a kind of way of telling you, yeah. Can you imagine that you are measuring something, but the thing you're measuring, you know you're not accurate to a million decimal places, right? You can only measure it to the tolerance of the machine, you know, the roller, whatever it is you're using. So d theta would be a measure of your accuracy. If you calculated all of this with the theta that you're talking about, dy would tell you how far out your answer could be. So if I measure the length and it's plus or minus 0.1, this guy here might tell me that my answer is plus or minus 0.3. In other words, a change in one affects the answer, right? So for any given function, a little difference in the x's won't not change the differences in the y's that you get. So this is essentially a way to estimate the error in a calculation. So if you want to know a reason for finding. So here is question 14. Y is equal to the cosine of pi x. And we're being asked to find dy. So nothing too strange. You differentiate this guy, you get negative the sine of pi x. Remembering that it's a chain rule, so the derivative of pi x gets me pi, so there's our answer. And so the differential is negative pi, the sine of pi x. Now suppose I tell you that x is 0.2, but I'm only sure, because I had to round it off, that the differential was, let's say, that guy. So it could be anywhere between 1.19 and 2, right? That's essentially what that means. Right? So can you imagine that here is 0.2, and they're only having a one side here, so this would be 0.19. So somewhere in that range, agreed, is the real value. So what would be the error? Not the answer, but what would the error be? That's what dy is telling us. Oh, by the way, dx. Well, dy is negative pi, the sine of 0.2 pi times negative 0.01. And so I would get a value here. Let's see, negative pi, the sine of 0.2 pi times negative 0.01. And the answer I got is that the differential is 0.018. So if I was going to evaluate the cosine of pi x at x equals 0.2, but I could be anywhere between here and here, then the range in my answers, right? The error at most will be that. So wouldn't I be pretty comfortable that the first decimal place would be right? And pretty much most of the second decimal place would be right. So differentials allow us to predict likely errors in a calculation if we were rounding things off. Okay. Any questions? Let's do another one. Which one shall I pick? Okay, let's pick 16. The function that we're going to find a differential for is going to be that guy. I would hope when you look at this, you don't have a problem. It's a quotient rule, pretty straightforward. So it's going to be f dash g, take away f of g dashed, all over g squared. It's going to be 1 times x take away 5, subtract x plus 5 times 1, over x minus 5 squared. What does that get me? X take away 5, take away an x, take away 5. Those x's cancel, those two numbers give me negative 10. So first stage of the process is find the derivative. Then you find the differential. And that's your done part A. And then in part B, they tell you that you're going to evaluate this function at 6, but it could be within 0.01 of 6, right? So it could be anywhere from 5.99 to 6, right? That's the best you can say for accuracy. How much error would your answer get you? Well, negative 10 over 6 take away 5 squared times negative 0.01. And that guy is negative 10, that's 1, and that's negative, so it's positive, and I believe you get positive 0.1. So if you evaluate this function close to 6, but you're not sure it's exactly 6, right? Because it could be as low as 5.99. The worst you're ever going to be is 0.1 out from the true answer. Whatever the real answer of x happens to be, the worst you'll be is 0.1. So if you're an engineer and you've got some ugly function and you know that x is 0.7 and delta x is, I don't know, 0.5, so that's an engineer rounding off, isn't it? Anywhere between 6.5 and 0.7, I'm going to call it that. If your differential is 0.003, aren't you going to be pretty okay with calculating with that value of X. Right? Your answer's not going to be miles away. On the other hand, if dy ends up being the number 42, aren't you going to be really very wary of doing that calculation? Because you could be 42 units out, and if the answer's 4 plus or minus 42 is not a good idea. Okay? So you need to know, if you can do it at least, an estimate of the errors that you are likely to generate in a calculation when you don't know the true value of X. If that's if that's your error, you're good. If that's your error, just don't do the calculation because your bridge will fall down. Did I tell you the joke about the Olympic College engineer students doing a competition to build their own aircraft? Okay. While I'm doing this, you can do your attendance. Olympic College engineer department had a project to do, and it was to design an aircraft. And it was run by Boeing, and they became one of the 3 finalists. The engineer professor took went to Boeing to see about whether they were going to win and take, the prize. And when they arrived, Boeing, showed them around the factory and done all sorts of cool things and took them onto an aircraft. And they were sitting down, and while we were there, the Boeing guy says, well, I'm glad to see that we've got 3 finalists, and we're going to tell you who the winner is in a minute. And he looks at the OCE professor and the 2 other university professors, and he went and said to him, you might not know this, but what we actually did is we used your students' designs and we built their aircraft, and you're actually in the aircraft that they designed, and we're going to take off and fly down to down to Vegas and give you a prize. And the minute they'd finished, the UW professor throws his hands in the air, starts screaming, and rushes out the aircraft. And then the UCL professor goes all white and starts mumbling and walks off the aircraft, trembling. And the OC professor is sitting there with a big smile on his face. And the guy looks at him and says, aren't you a little bit worried that your students have designed the aircraft that you're going to be flying in? And he shook his head and says, I have no problems at all. He says, if it was my students who designed this, there's no way in the world this aircraft is leaving the ground.
That's funny.
Was that, oh, you like that one? Are any of you going to be aeronautical engineers?
Yes, I am.
Oh God, you poor soul.
So funny though, because right now we're in the engineering club, and they're trying to they're doing this thing with CU Boulder, and we're making a satellite.
So there's no way in the world that's ever going to take off, right? Okay, well, thank you, everyone. Your test is there. You know the usual thing. I guess I'll give you pre-warning. You know that we only have 2 more weeks to go. This is week 5 finished. I would suggest, I know it's hard for you because you've got other commitments, but you should start thinking about preparing for the event. So even if it's just getting organized about what days you're going to spend some extra time, you need to get that sorted out. Because it's a week on Thursday, if you want really scared. Right. So we've all next week, we're doing new stuff. The week after that, we'll be doing mostly new stuff. and on Thursday we'll be doing your final. And it's 30% of your grade, and you want to make sure you do, the best you can. Well, that's it. Bye-bye. And you can hang about and ask me questions at the end. Hi, Tessa.
Hi, I do have a question about some of the set notation. No, it's interval notation on on one of the assignments, but I don't have it open. So give me just 1 second to open it.
No problem. Okay. Once you've owned it, if you don't mind, I'll let you share the screen. That way you can show me the question and we can look at it together.
That will be perfect. Because I think I've danced maybe all around it, or at least I hope I have.
What section is this question from?
I believe I am in let's see, we did 3.7 and then we skipped to 3.9.
Yes, correct.
Right?
There is no 3.8 just has exponential growth. We don't need to worry about that.
No, it must be in 3.7 then. I'm sorry. So it's in 3.7.
Okay, rates of change.
Yes, the rates of change.
Okay.
And it's opening, and then okay, so let me go share my screen. Oh, the screen sharing is disabled for the moment.
Oh, I haven't done that. My apologies. Okay, you should be able to share it in a moment.
Okay. And I want to share that one. Okay, so I believe
Question 10.
question 10, and there's one other one where I've put in a multitude of answers.
Okay, so we'll go to whatever is the first one you want to look at, and we'll check it.
Okay. Oh, it's this one. It's this one. Okay, so 10 is the first one, and then I think there's one more. So
the question was asking, when is the particle moving in a positive direction, right? So if you could scroll up to, oh no, you can't scroll. This one doesn't have a picture, does it? No.
It doesn't. I think
No.
you have to put it in Desmos.
Right, now, if you put it into Desmos, then what you would discover is that it's what is it? It's going to be.
It's a cubic.
Well, it's derivative. Yeah, it's a cubic, but its derivative is a quadratic, right?
Yes. So I would be using the velocity
Derivative.
function
Yeah.
instead of
And
the
you'd be
position function.
yeah, correct.
Okay.
And you'd be looking for when is the velocity positive. So if you can imagine, I'll take control.
Okay.
And kind of show you what I'm getting at.
Yes.
If I'm not saying this is the right answer because I haven't done it in my head. I can't do that in my head, but
Okay.
whatever.
I did find I'm gonna have to go back and review these anyway, because I did find myself using Desmos quite a bit, and then I was I got myself really turned around is what I did.
Can we pretend that that's what the derivative function, right? It's a quadratic, and there'll be a point here and there'll be a point here, and this is 2 and this is 4.
Yes, that's right.
In time starts at 0, so we don't care about this side, but time does continue forever. So we're allowing that direction. So if I'm looking for when is this positive, as long as you're between here and here and forever.
Okay.
Right? And this interval is 0 to 2. Union, this interval is 4 to infinity. So when they talk about interval notation, they want you to do that. They don't mean that. That's not interval notation.
Okay. I think I got it confused with some other ones. And then also I was looking at the position. Oh, just a little bit. Can you hear me?
Cannot hear me. Okay.
I can hear you better now.
Okay. For some reason, my mic is being weird today. So that's what they need you to do. So
Okay,
find the velocity function, put it into Desmos and find out when it's positive. Now, if they wanted to know when is it going in a negative direction, the answer would be a little bit easier. It'd be from 2 to 4.
between 2 to 4, but use velocity function, not the position function.
Correct. Because the position function being positive and the position function being negative don't actually tell you
The velocity.
what direction you're going, because if you imagine this as your time and your position function, it goes up and down and does things like that. And I'm not quite sure what a negative position function would mean. I guess it would mean I'm to the left of where my house is, right? And positive would be to the right. But
Right.
positive is going uphill.
And again,
So
we're just
that-
talking about the velocity function, not the position
Yeah.
function. Okay,
Right. Yeah. If you wanted to use the position function, you could. You just have to identify these 2 key points, because from 0 to 2, it's going uphill, and from 4 onwards, it's going uphill. So a position function going uphill means you're going in a positive direction. A position function going downhill means you're going in a negative direction. It's easier to use the velocity function, because then that question just becomes, when is it positive or when is it negative? And that's just easier to deal
it
with.
simplifies it a little bit. I think that must be what I did, is I must have flipped back and forth and actually arrived at some answers. And so I need to go back and visit that one again.
Right. Your answer to C was a help, because in the answer to C, they told you at 2 and 4 seconds. And so you knew it's something to do with 2 and 4. And if you look at this, then you see that why it's 2 and 4, which is
Yeah.
the numbers I was using. Okay,
Well, I
what was
actually
your-
got the points from the graph, but then I think I was flipping back and forth between the graphs is what happened, and definitely confused myself with those. And then I think there's one more on there.
Okay, I'll let you share again.
Let me see if. Oh, it's still at the bottom of,
Okay, so we're
10.
talking speeding up and slowing down now, right?
yes, and I think I understand what we're talking about, but I might be confused within the graphs and then which intervals, because I thought that I had the correct intervals in some of my attempts, but it didn't like what I put in. So I might be
Okay.
looking at the wrong graph again, is what I'm thinking now.
Well, when you do speeding up and slowing down, you're really using information from 2 different graphs. You're using velocity and you're using acceleration.
Mhm.
So let me show you how you would put that together.
Okay,
So if you did a number line, right, basically based on this guy,
Mhm.
you start at 0, at the 2-second mark, and then there's a 0 velocity there at the 4-second mark, and off you go forever. You will find that here it's positive, here the velocity is negative, and here the velocity is positive. So that's basically me doing a little timeline for the velocity function, right? A little horizontal line. Now, if you go and you do acceleration, I believe the acceleration is 0 at the 3-second mark. And I'm guessing. I think it is negative in this side and positive in that side. It's one or the other. If this is wrong, just switch places. Now, once you know velocity and acceleration, you can then figure out when things are speeding up and when things are slowing down. And the way you do it is you find zeros, 0 velocities, 0 accelerations. It doesn't really matter, but whoever is 0, because at zeros, things change from one to another. So that's why 0 is important. Now,
Okay.
from 0 to 2 seconds, the velocity is positive and the acceleration is negative. So if I call these A, B, C, and D, right? In region A, since one of them is positive and the other is negative, that means you're slowing down. Now in region B, both of them are negative, right? And when both of them are the same, in this case negative, then you're speeding up. In region C, there's one of each, so you're slowing down again. And in region D, they're both positive, so you're speeding up.
Okay.
So the trick to speeding up and slowing down is when are both of them the same, right? Velocity and acceleration. When are they
Mhm.
both the same? That's speeding up situations. And when they're not the same, that's slowing down. So now we have to figure out, let's suppose you want to know speeding up. Speeding up happens between 2 and 3 seconds.
And then in
And
union with
anything from 4 onwards.
to infinity. Okay.
And then
All
if you do the slowing down, just for completeness, you're going to be slowing down from the 0 to 2 second mark and from the 3
To
to the
4.
4 second mark.
Okay.